Dear participants, the EFFECT team warmly welcomes you to this fourth module on cost effectiveness and efficiency analysis in education. Successfully completing this module will allow you to define the concepts of efficiency and cost effectiveness, get introduced to cost-benefit analysis in a public context, calculate costs and benefits in practice, and apply these concepts to a specific example. This module should also allow you to master theoretical concepts such as efficiency or cost effectiveness, know how to apply these concepts in practice in cost-benefit analysis in a public context, and practice these applications in exercises and in Excel. Dear participants, welcome to Module 4.1, in which we will define efficiency. In a publication issued by the European Commission, efficiency is defined as follows. Efficiency is about the relationship between inputs and outputs in policies, programs, projects, services and organizations. Modern public administrations manage their processes and available resources to achieve the best results for their communities, value for money, and sound financial management. If we want to provide a mathematical definition for efficiency, efficiency can be formulated as the quotient of outputs and inputs, and therefore, for an efficient use of resources, we would hope for the ratio to be close to 1, but both inputs and outputs can be very difficult to measure. In education policy, inputs could be the teaching staff, funding, infrastructure, or policies. Whereas outputs in education policy could be school attendance, dropout, motivation, test scores, or students' health. Dear participants, welcome to submodule 4.2, in which we'll define cost effectiveness. Effectiveness is also defined by the European Commission publication and concerns the extent to which objectives have been or should be achieved due to the policy, program, project, service, or the organization's activities. Increasingly, administrations are expected to exhibit results orientation, to select and implement the instruments to achieve high-level objectives and meet societal needs. Based on this description, we can define effectiveness as to what extent previously defined goals have been achieved by policy, program, project, etc. And if now we apply this definition to cost effectiveness, we get that cost effectiveness describes to what extent previously defined cost goals have been achieved by policy, program, project, etc. Dear participants, welcome to submodule 4.3, in which we will introduce cost-benefit analysis in a public context. Cost-benefit analysis can be defined as an instrument for comparing the benefits obtained through a program or intervention vis-à-vis its costs. CBA compares the advantages deriving from a decision, a program, policy, or intervention with the costs that are necessary for implementing the decision itself. As you can see from this definition, first, costs and benefits also include non-monetary costs and benefits, and time matters. We will discuss both elements later on, but these are very important. Indeed, examples of benefits to take into account do not only include monetary benefits, meaning financial returns, but also social benefits, such as the improved transmission of human capital or the reduction of social costs, such as less dropout. The same applies for costs. Costs do not only include the costs of implementing the decision, but also human costs, such as teachers needing to work overtime to implement the policy, or social costs, such as higher failure rates in a better but more demanding grading scheme. Based on our intuition, let us adopt for now a first decision rule. We want social benefits to be bigger than social costs, and therefore, we need the benefits strictly larger than the costs, which is a decision rule that we should keep in mind. Dear participants, welcome to submodule 4.4, in which we will start formalizing cost-benefit analysis. At the end of last module, we established a first decision rule. which is benefits strictly larger than costs. Let us now define the net benefit, which are the costs subtracted from the benefits, and the benefit cost ratio, which is given by the fraction of benefits over costs. The net benefit and the benefit cost ratio are both metrics, which means that they can be computed. If now we combine our decision rule with our metrics, we get that this decision rule is validated using the net benefit metric if the net benefit is strictly larger than 0. Dear participants, welcome to submodule 4.5, in which we will continue to formalize cost-benefit analysis. Let us keep in mind that during module 4.3, we established the first decision rule, which is the benefits need to be strictly larger than costs. And during module 4.4, we defined the net benefit as costs subtracted from benefits and the benefit cost ratio as the fraction of benefits over costs. Both the net benefit and the benefit cost ratio are metrics, which means that they can be computed. Let us now combine our decision rule with the benefit cost ratio metric. The decision rule is validated with the benefit cost ratio metric if the benefit cost ratio is strictly larger than 1. Therefore, a public project, a public policy, public decision should be implemented if net benefits are strictly larger than 0, or equivalently, if the benefit cost ratio is strictly larger than 1. Dear participants, welcome to submodule 4.6. As you might remember, in submodule 4.3, we discussed that time matters in cost-benefit analysis. And today, we will start to understand why this is the case. To understand this, let's have a look at the following phenomenon. It is often said that €1 today is not equivalent to €1 in 1 year, but why? Let us consider a sum of €100 and a 10% interest rate. If now person A receives this sum today, this person can put the sum on their bank account, which leads to €100 on their bank account. However, after 1 year, this €100 have generated 10% of interest, and therefore person A has €110 on their bank account. Let us now consider the case of person B, who also receives a sum of €100, but in 1 year. If person B now puts €100 on their bank account in 1 year, their bank account next year will only be of €100 and not of 110. Indeed, if we compare person A's and person B's bank accounts in year 2, we have that person A has €110 on their bank account, while person B only has €100 on their bank account. Therefore, the money on their bank account is different based on the moment in time in which the sum was received, which shows that time matters. Furthermore, the interest rate seems to play a crucial role. Let's keep this in mind. Dear participants, welcome to submodule 4.7, in which we will continue to understand why time matters in cost-benefit analysis. Let us come back to person A, who received a sum of €100 at a 10% interest rate, and we further suppose this interest rate to be constant. What happens if person A keeps their savings longer than 2 years on their bank account? After 2 years, we had €110 on their bank account. After 4 years, we have the initial €100 times 1 plus 10% times 1 plus 10% times 1 plus 10% times 1 plus 10%, which then yields approximately €146. Or to put it simpler, we can also write it as €100 times 1 plus 10% to the power of 4, which leads to exactly the same result. After 9 years, we will therefore have the initial €100 times 1 plus 10% to the power of 9, which then yields an approximate amount of €236. We can generalize this into a general formula, which is FV equals PV times 1 plus R to the power of T, with FV being the future value of the amount of money PV after t years under the discount rate R, and therefore we managed to create a link between present and future value of an amount of money. Dear participants, welcome to submodule 4.8, in which we will continue to learn why time matters in cost-benefit analysis. We found that the future value equals the present value times 1 plus r to the power of t, which allows us to determine the future value of an amount of money based on its present value. However, what can we do if we want to determine the present value based on the future value? By algebra, we get that the present value is equal to 1 over 1 plus r to the power of t times the future value, which provides a possibility to determine a present value. Dear participants, welcome to submodule 4.9, in which we will continue to learn why time matters in cost-benefit analysis. During the last submodule, we found a possibility to determine the present value through the formula present value equals 1 over 1 plus r to the power of t times the future value. Now, let us have a deeper look at the factor 1 over 1 plus r to the power of t. 1 over 1 plus r to the power of t is the factor by which the future is discounted. The future is discounted means that differences in value between the present and the future are taken into consideration. If we have that 1 over 1 plus r to the power of t strictly smaller than 1, this means that the economic agent is impatient. But what if now differences in value between the present and the future do not only have financial reasons? Examples could be, let's say that a public institution needs financial resources or is impatient. In this case, the factor 1 over 1 plus r to the power of t includes this aspect as well. Dear participants, welcome to submodule 4.10, in which we will continue to integrate temporal aspects into cost-benefit analysis. In the context of public decisions, public projects, public policies, the trade-off between present and future value is rarely purely financial. Examples include educating children on healthy eating habits, which has both present and future value. It has present value for the children today, but it also has future value for the adult that the children will one day become. Furthermore, provide a budget for social events in high schools has rather present value, which means that for many events that happens in high schools today, it's mostly about giving students a great time today, but not that much about what happens to them in 3 years. The investment in adequate ICT infrastructure, however, is the future value. We have a huge investment today to have adequate infrastructure, which we can use over the next 5 years or 10 years to provide quality education to children. The value of these investments is not really that financial. Educating children on healthy eating habits aims to ensure public health, which is not really a financial value. It is, but it is also a huge social value. Providing a budget for social events in high schools aims to contribute to pupils' personal development, which is a non-financial value. Investing in adequate ICT infrastructure aims to provide high-quality education, which again will have somehow of a financial value because people that are well educated today will be able to make huge and great contributions to the labor market tomorrow. But we also want to provide high quality education to provide high quality education. We do not only do this for financial reasons. We also want to do this to allow children to reach the best of themselves, which is a non-financial value per se. As we have seen in public matters, value often exceeds a purely financial meaning, and therefore, let us integrate all these aspects in our notation by replacing the purely financial discount rate small r by the social discount rate small s. The huge difference between small r and small s is that small s accounts for all these social dimensions which may draw the difference between investing today or investing tomorrow. Dear participants, welcome to submodule 4.11. As we have seen, time matters in cost-benefit analysis, and therefore, in this submodule, we will start to establish an intertemporal decision rule, meaning a decision rule that takes these temporal aspects into account. Indeed, let us reflect on what we have learned so far. We have learned a decision rule: benefits must be strictly larger than costs. But we have also learned that benefits and costs might evolve over time, and therefore, the decision rule must be intertemporal as well, taking into account these temporal aspects. But how to achieve such an intertemporal rule? To do so, we use another tool from financial modeling, which is the net present value. The net present value discounts the sum of future values to get a sense of their present value. So what the net present value actually does is that based on a sum of future values or one single future value, it provides us the present value that this future value has today. To get a better picture of what this means, let us reconsider person A again. This time, person A is a school principal who is unsure about whether to renovate an old classroom of their school. If the classroom is renovated, it has a great quality afterwards, and another school principal who is desperately searching for additional classrooms for their school has already asked to borrow the renovate classroom half-time, which would then provide an annual rent of 50,000 euros to person A's school. Should person A now do this or not? To determine this, we would need a decision rule. But what would be a good decision rule? We will discuss this in the following submodule. Dear participants, welcome to submodule 4.12, in which we will continue our way towards an intertemporal decision rule. This decision rule will actually be based on the previously established decision rule, which was that net benefits is strictly larger than zero if benefits minus costs is strictly larger than zero. To now account for the temporal aspect, we consider the benefits and costs as the sum of the discounted benefits and costs, assuming a 10% discount rate. After having computed the discounted benefits and the discounted costs, we are able to compute the net benefits by simply taking the sum of all the discounted benefits and the net costs by simply taking the sum of all the discounted costs. The net benefits and the net costs that we have now computed allow to compute the net present value, which is given by the difference between the net benefits and the net costs. Renovating the classroom and lease it afterwards is therefore equivalent for person A to receiving 24,342 euros today, and doing it thus seems a pretty good idea. Dear participants, welcome to submodule 4.13. In the last submodule, we have discovered the net present value, and now we will establish a general formula for it. As we have done last time, we can compute the net benefits by taking the sum over all of the discounted benefits, and we can compute the net costs by taking the sum of all the discounted costs. If we note BT the benefits in year T, CT the costs in year T, and if we assume a constant discount rate R and a final period capital T, we can define the net benefits as the sum from t equals 0 to capital T, bt over 1 plus r to the power of t, whereas the net costs are given by the sum from t equals 0 to capital T, ct over 1 plus r to the power of t. And this provides the following general formula for the net present value. Net present value thus equals net benefits minus net costs, meaning the sum from t equals 0 to capital T bt 1 plus r to the power of t, minus the sum t from 0 until capital T of ct 1 plus r to the power of t. As you can see here, we have used r and not s to be the discount factor, which means that in the first time, we only locate ourselves in a financial setting. From this previously gained general rule, we can now obtain a new intertemporal decision rule. If we want benefits to be strictly larger than costs, then we want the sum t from 0 until capital T bt 1 plus r to the power of t to be strictly larger than the sum t equals 0 capital T ct 1 plus r to the power of t, which then implies that net benefits are strictly larger than net costs and could be reformulated as the net present value being strictly larger than 0. Here again, we see that we have used R to be the financial discount factor. If we want to apply this to social setting, we only need to replace the financial discount rate R by its social discount rate equivalent small s. Dear participants, welcome to submodule 4.14, in which we will learn how to estimate the social discount rate. We already considered the social discount rate as the discount rate which also takes social aspects of the differences between today and the future into account. But how can we compute this social discount rate? So far, we have always considered the social discount rate as given, but how could we estimate it in practice? Several authors have tried to deal with this question, and we will discuss some of their approaches in the following. A first approach is provided by Andrew Kaplan and John Leahy, who describe that the standard proxy for the social discount rate is the market discount rate, meaning the financial discount rate. But they also acknowledge and even prove in their article that policymakers should be more patient than private actors, and therefore this comparison is not that well fitting actually. Dear participants, welcome to submodule 4.15, in which we will continue to learn how to estimate a social discount rate by considering another approach. This other approach is the approach presented by Sethilmus and Akbulut, who provide some estimations of social discount rates for developed countries, mostly ranging between 3% and 5%. They then present a social time preference rate approach, which considers the social discount rate as an opportunity cost of consumption. Thus, they define the STPR, which can be seen as an approximation of the social discount rate. Here, P is the utility discount rate, meaning the intertemporal opportunity cost. E is the elasticity of marginal utility of consumption, which can be calculated based on personal taxation of food demand. And G is the growth rate of per capita real consumption, which is often estimated using time series data. Dear participants, welcome to submodule 4.16, in which we will apply cost-benefit analysis to a case study, namely a case study on elite schools in Hungary. This case study is based on the article Does It Matter When Your Smartest Peers Leave Your Class? Evidence from Hungary, written by Dr. Fritz Schilz, Professor Denis Mazrekas, Professor Daniel Horn, and Professor Christoph de Witte, who found that one additional high-achieving student leaving primary school to get enrolled in an elite school reduced the mathematics test scores of the remaining students. And this can indeed be linked to social costs. A priori, most people would consider bright students to be enrolled in elite schools a great idea, because their talents can often be better supported there. But Dr. Schilz and his colleagues showed that bright students leaving primary school leave a negative impact on their former classmates, which creates a non-monetary social cost. And therefore, we can use this example to illustrate the difference between financial and social costs. While financial costs would be the cost to pay a specialized tutor who might be able to teach the bright student in their old school, social costs might be the cost in terms of test scores the former classmates have to pay. The main point of this example is to say that if we only focus on the financial costs, then the computation would be very clear. Rather than paying a specialized tutor who might be able to appropriately teach the gifted student, this student should rather be sent to an elite school where they can be adequately taken care of. However, the computation changes once the notion of social cost intervenes. In this case, we do not only have the cost of paying for a specialized tutor if the student stays, but we also have another cost. The cost in terms of test scores the remaining students have to pay. Therefore, while at first sight, only the alternative of the bright student staying at his old school seemed costly, including social costs into the analysis makes it appear that indeed both alternatives are costly. Dear participants, welcome to submodule 4.17, in which we will illustrate cost-benefit analysis via another case study, namely a case study on summer schools in Flanders. This case study is based on the article The Resilience in Test Scores and the Mitigating Effect of Summer Schools 1 Year After the COVID-19 School Closures, written by Letizia Gambi and Professor De Witte, who found that summer schools, which were mainly targeting the most vulnerable students, were successful in keeping the most vulnerable students from falling further behind in learning. And in this context again, it could be argued that organizing summer schools only creates financial costs, such as teacher salaries, heating the schools during the summertime when otherwise it would not be necessary, and that summer schools should therefore not be organized. And again, this would exclude a part of the problem. As highlighted by Letizia Gambi and Professor De Witte, summer schools can avoid socially disadvantaged students from falling further behind. And therefore, even if there might be no financial benefits to be obtained from summer schools, there are still other kinds of benefits to be derived from summer schools, which are the social benefits. On this slide, you can see all the different sources that have been used to establish this fourth module. The EFFECT team thanks you for having completed Module 4 on cost effectiveness and efficiency analysis in education, and hopes to welcome you soon for Module 4b on machine learning. If there are any remaining questions, suggestions, etc. regarding this module, please contact Professor Dr. Christoph de Witte, who is the main coordinator of EFFECT and the director of the Lehr Research Group at KU Leuven.